Over the last few lessons, we've been looking at motion in terms of investigating displacement time, velocity time, and acceleration time graphs. Now we're going to be looking at equations that also describe motion. Here we'll be looking at motion in one dimension. These equations here appear on your formula sheet, and they apply for situations where we have constant acceleration only, except for the very first equation you get given. The first equation is actually the definition for the average velocity. So average velocity equals displacement on time. So we looked at this quantity when we were describing motion to begin with. What you don't get told here is there is another formula for average velocity for this condition that we have constant acceleration. That is, the average velocity is equal to the initial velocity plus the final velocity divided by 2. We'll look at a graphical link to this shortly. The next equation, final velocity equals initial velocity plus acceleration times time. There's a couple of ways we can think about this. I like to think of it as the final velocity equals the initial velocity plus a change in velocity. And that's exactly what this acceleration times time term is. It represents a change in velocity. Why? Because acceleration is the rate of change of velocity, so it could be 2 meters per second per second. That means that the velocity is changing by 2 meters per second each second. So then if that change happens for, say, 3 seconds, you can determine the change in velocity. Another way we can come up with this equation is just by the definition of acceleration. So the acceleration is the change in velocity on time, which is v take u on t. Then if we rearrange this equation and make v the subject, we get our above equation of motion. There are two other equations of motion you get on your formula sheet. You might have seen this one last year. However, this one most likely is new. We'll discuss the one on the right in more detail later, but the one in the middle you can obtain by this equation, v equals u plus at, and the last one. In this equation here, if you make t the subject, you get t equals v take u on a. You can then eliminate t in the last equation by subbing this expression in. Then, with rearranging a little bit of algebra, you can show that it equals this equation here. So the 5 quantities that we see above here are initial velocity, final velocity, acceleration, displacement, and time. You'll see that each of these 3 involve 4 variables. If we're going to use one of those equations, that means we must know at least 3 of these 5 variables if we're going to predict any motion in the future. The tricky bit here perhaps is picking the right equation to use. What you'll see that each one of these equations, there's a quantity not involved. See how this equation doesn't have displacement? The next equation doesn't involve time, and the last equation doesn't involve final velocity. So sometimes picking the correct equation to use, it can be handy looking at which quantity is missing from what you know, and then picking the one with the corresponding quantity missing. Very important to remember here that these 4 quantities are all vector quantities, which means they have a direction. Because this is motion in one dimension, we're going to use positive or negative signs or directed numbers to indicate a direction. We'll talk more about this in the example. Let's have a quick look at these 2 equations in terms of a velocity time graph. Here we have a velocity time graph with constant acceleration. So we see a straight line which has a constant rate of change. And remember, the rate of change of velocity is acceleration. So indeed, we have constant acceleration. If we look at the slope of this line, that's where the first equation comes from, v equals u plus at. However, in the previous videos, we saw that the area underneath the line is equal to displacement. So what we can show is that the displacement, the area under the curve here, is equal to ut plus a half at squared. Let's break this into two shapes. The first being the rectangle. The area here is equal to u times t, so the height of the rectangle times the run. So there's our first term in our expression above. The next one is a triangle. Now the area of a triangle is a half times base times height. So here the base of our triangle is just equal to t. Now the height of our triangle from u to v is simply a change in velocity. Now we looked at before, a change in velocity is equal to acceleration times time. So simplifying here, we see the area of that triangle is a half at squared, giving us the second part of the expression above. So remember here, these equations only work for constant acceleration, because if we had an acceleration that was high initially and then decreased to the same final velocity, can you see here that the area that I'm shading is no longer the area of a triangle, so our formula wouldn't work. You won't need to prove this in the exam or in a test, but it is handy to make the link between your previous knowledge and the equations that you'll use quite a bit. Let's have a look at an example. A snowboarder in a race is travelling at 10 meters per second north as she crosses the finish line. She decelerates uniformly, coming to a stop over a distance of 20 meters. Let's unpack this a little bit. So I see here that I am given a direction, so north. That's prompting me to, at the end of the question, to go back to the compass bearings to describe any direction I'm given. Here I see a term that we use every day, decelerates. That means the acceleration is in the opposite direction to the initial velocity, north. So here, my acceleration is in the southerly direction. Again, uniformly is just another word for saying the acceleration is constant. It's not changing. We see that the snowboarder is coming to a stop. That's telling me the final velocity is 0 meters per second over a distance of 20 meters. Remember, in our equations, we use displacement. However, most of the time in one dimension, you'll see that the distance travelled and the displacement are commonly going to have the same size. So here they're both 20 meters. The direction of my displacement though, here is going to be north. Before we even look at the first question, let's write down the information we know. First, I'm going to give a positive direction. Here I'll let north be positive. The initial velocity is north, so that's positive in my chosen positive direction. Here I'm making it obvious to the person marking or looking at my work that I understand that this quantity is a vector quantity, and it's really important that I show a direction here. Final velocity is 0, and the displacement is plus 20 meters. Important to check here that the units are all consistent. I have meters for my displacement and meters per second for my velocity, so it's all good here. Sometimes you might need to convert between kilometers per hour to meters per second, or perhaps kilometers to meters. In the first question, let's calculate the acceleration of the snowboarder as she comes to rest. So looking at the four quantities I have here, it doesn't involve time. So the equation of motion I'm going to be using is, now substituting in my known values and simplifying. Now I just need to solve for A. So here I get an acceleration of minus 2.5 meters per second squared. Remember, you can always look at your information sheet if you're unsure about the units for acceleration or any quantity. Also, we see that the acceleration is negative. That means it's in the southerly direction. It is expected in a test that you'd return to this direction, so your final answer should be 2.5 meters per second squared south. Now another question. So I've recorded the acceleration that I have just figured out. So that's minus 2.5 meters per second squared, indicating the southerly direction. And I don't know time. So now let's calculate how long it takes for the snowboarder to come to rest. So we need to pick an equation. So here we could use either of these equations to find t. So the first one, v equals u plus at, we know the final velocity, initial velocity, and now we know the acceleration, so we can solve for time. In the second equation, we know the displacement, the initial velocity, and the acceleration, so again we can solve for time. But this second equation, if I sub in, I see that I have a quadratic equation in t. So here, unless you're going to use the general quadratic formula, this is difficult to solve. So in general, we use this equation to solve for t only if the acceleration is 0 or the initial velocity is 0. Because in both of those scenarios, it simplifies the equation and we don't have a horrible quadratic to solve. So if you can avoid this equation by finding the final velocity, you'll see that we can use v equals u plus at, and it is much simpler. So let's substitute in. Now going through our steps to solve. And we get an answer of 4 seconds. Now, before you get started on the question set, just remember that converting between kilometres per hour to metres per second, you divide by 3.6. In the textbook, there's also another equation of motion that you don't get given. So the displacement is equal to velocity times time, the final velocity, minus a half at squared. Looking at the velocity time graph, we can see that this is true because velocity times time gives us the area of this large rectangle. And we already know that a half at squared is the area of this triangle, which is also equal to the triangle above it. So if we take the area of the rectangle and subtract the area of the triangle, we see we're left with the area underneath the curve. Sometimes it might be useful to remember this equation. However, you don't need it to solve any questions that you'll be given. But most of all, please remember to assign a positive direction. It is really this step here, when the questions get harder, that lets me know that you understand the question. The solving of the equations don't get you many marks. This is the vital step.